please? Hello, everybody. Thank you, everybody, for signing in to our Hioki webinar of today. Today's topic is lithium-ion batteries and the renewable energy future. I am Chris Schultz. I'm the product manager of Hioki USA, and I will be moderating the session today. You probably have heard that it's all over the news. Yeah, lithium-ion technology plays a key role in sustainable energy today. Every day we hear news articles about lithium-ion. In this webinar, we're trying to shed some light on the technology behind the news and provide you some insight in the complex topic of renewable energy, the role that lithium-ion plays in this overall scheme. And we're looking at it from an engineering perspective. Before we begin, I'd like to start with a quick poll to let you all settle in and get a few more people to sign up. Okay, let's start the poll. There's a live poll coming up. So a question that I'm interested to know is, what industry are you joining from? Are you from the electric utilities? Are you doing battery research and manufacturing? Are you working with automotive and EVs? Are you in test and measurement industry? Are you a student? Or are you in none of these categories? Next thing I'm interested in is where you're joining us from. Is this from North America, South America, Europe, Africa, Australia, Oceania? And the last thing is, if you could travel for vacation in time, anywhere you want, which period would you go to? Would you go to the past? Would you go to the future? Or would you stay where you are today? Let me give it a few more minutes for everybody to reply. Thank you for all the responses come in. Yeah, rowdy crowd. Right, perfect. Yeah, we still got the needles moving, but it's going to a stable position now. Okay, thank you. Let's end the poll here. And here are the results. So it's a mixed bag of attendees that we've got. Some of you are in electric utilities, others in battery research, automotive test and measurement, bubbling up a little bit, and then a fair amount of students. Welcome, everybody. I think we have something for everybody in this webinar. High concentration North America and Europe. Welcome. And then people would love to travel to the future. Great. That's interesting. So yeah, we're looking in the future in this webinar. All right. Thank you, everybody. So let me take the opportunity to give just a few words about Hioki. Hioki was founded in 1935. This is just a few years before all of the other major test and measurement companies. Hioki is headquartered in Ueda, Japan. We are the world leader in the test and measurement industries that we engage in. We are leading through innovation, advanced design, domestic manufacturing in Japan, and local sales and service. So for example, when many of our competitors talk about carbon neutral or being carbon neutral, we have been carbon neutral since April the 1st of this year. Our instruments are built in a carbon neutral facility today. We offer over 200 main products that are known for their safety and quality and meeting an expensive range of application. We contribute to the efficiency and value of our customers' work in research, development, production, and electrical maintenance. We operate worldwide, and we'll give you some detailed information on how to contact us locally at the end of this presentation. I want to mention a few more housekeeping items. We will have a moderated question and answer session at the end of the presentation. So there will be a presentation and then a moderated question and answer session. So feel free to type in your answers down in the bottom of the screen. You see a question and answer button. type in your questions there if you have any. We have a panel of experts standing by that will answer some of the questions as you type them in. And we will also review these questions at the end of the webinar. We will have some poll questions throughout the sessions, so I hope you participate. Some of them fun. We'd love to hear who you are and what you are thinking of. So I hope you participate in the poll questions. The session will be recorded. It will be recorded 24 hours after today on our website. That's at yokiusa.com/webinars. Go to the Knowledge Center. There's a lot of important information in the Knowledge Center, and then navigate to the webinars, and you see all our recorded webinars in that session. With that, it is my distinct pleasure to introduce today's speakers of the webinar. First and foremost, we have a guest speaker. This is Jill Pestana. Jill works as a senior scientist. She's developing lithium-ion battery technology, and she is an inventor of patents related to battery technology. Jill earned her master's degree in material science and engineering and has a bachelor's degree in physics. Jill is also the creator and host of the YouTube channel Across the Nanoverse, and I encourage everybody to check that out. It's a really fun and exciting channel, Across the Nanoverse. In the channel, she shares educational content of her expertise. In addition, Jill is very engaged in social issues. She is the founder of the STEM Thrive Guide. STEM stands for Science, Technology, Math, and Engineering. In the STEM Thrive Guide, she provides supports and guidelines for targets of harassment in work and at school. So I'm very excited about having Jill as our guest speaker today. Next is Ihsan Daljic. He's an application engineer at Yoki, where he's responsible for providing daily support to a technology question. So you might have talked to Ihsan already when you called our hotline. In addition, Ihsan manages our virtual demo lab. We can test out our instrument virtually anytime, pretty much. The virtual demo lab is located in Dallas. Ihsan worked as test engineer for Maxim for 8 years, and he worked as application engineers for DFW Test for 13 years before that. Ihsan has a bachelor's degree in electronics and electrical engineering from the Trinity College in Dublin. Today's panel is Barry Bowling and Kevin Lee. Barry is a senior applications engineer with Yoki. He specializes in industrial and power application. Barry hails from Atlanta. And Kevin is our applications engineer in California. Kevin specializes in battery technology. So very powerful panel. I'm sure we can answer any question that you may have asked. So without further ado, I want to turn over the mic to Ihsan. Ihsan, please tell us everything about renewable energy and the role of lithium-ion batteries.
Thank you very much, Chris. I shall certainly do my best. And thank you everyone for attending. Without further ado, let's get started. So first of all, what is renewable energy? So renewable energy is from natural sources or processes that are replenished. And they're replenished within a human timescale versus, for instance, fossil fuels, which are used up far more quickly than they're replenished. There's two main groups of renewable energy. You have variable renewable energy. It's also known as intermittent renewable energy sources, or IRES. But in this webinar, we'll use VRE and variable renewable energy interchangeably. Some examples are solar, wind, coastal areas. They can use tidal power and waves to generate electricity. With variable renewable energy, the power output can't be controlled by the operators. It's dependent on external forces of nature. So we can't really control the output. On the other hand, we have dispatchable renewable energy. This is where sources of power can be adjusted or dispatched on demand. And so we're all familiar with hydroelectric power, for instance. It's been around for decades and it can make significant amounts of power. But around the world, most of the good sites for large-scale hydroelectric have already been developed. Then we have geothermal energy. Again, this has very severe geological or geographical limitations. For instance, Iceland can meet 65% of its energy needs with geothermal energy and 25% of its electric production. But their unique geology allows easy access to geothermal energy. Biomass, on the other hand, comes from burning material that's produced from biological sources, usually byproducts and waste material. The carbon neutral status of biomass is under debate. So for this webinar, we're going to be focused on variable renewable energy, or VREs for short. So the chart here on the left is from REN21, organization called Renewables Now, which they're an organization in support for the transition to renewable energy. So we can clearly see in the year-to-year additions of renewable energy power capacity, it's been increasing every year. And right now, in 2019, more than 200 gigawatts of power were added. So the main drivers for development have been obviously the technology cost decline. The cost has come down, especially for photovoltaic cells. And if you look on the chart, you can see right around 2015 and 2016, solar starts to really beat wind power in terms of installed capacity. Then we also have supportive policies by governments around the world, especially the Paris Climate Agreements, for instance, where they have imposed targets for reducing greenhouse gases. And these are only really achievable by going towards VREs, variable renewable energy. And there's also private sector sustainability goals. I mean, case in point is that Chris mentioned that Hioki head office has transitioned to 100% renewable energy since earlier this year. And obviously, the big challenge here is the crucial need to reduce our CO2 emissions to avoid disaster. So I'm going to talk a little bit about some of the challenges of deploying VREs into existing grid infrastructure. So existing grid infrastructure has been designed around dispatchable energy, where electricity is generated as a just-in-time commodity. So as the demand for power fluctuates, more power can be dispatched to the grid. So when you have a small percentage of VRE within the whole grand scheme of things, the impact of VRE on the grid is negligible, because most of the time the grid will absorb all the electricity produced by renewables because there's sufficient demand for electricity. And also, since wind and solar, for instance, they have no fuel costs. So grid operators like to use them first when they're available. And so the grid operator then makes up the net load, which is the total demand, using dispatchable energy. And so only during like very rare events is the production from renewables would exceed demand, requiring it to be curtailed. However, as the percentage of VRE increases, we can easily get to a point where our dispatchable power capacity is not sufficient to bridge the gap. So, for instance, when the wind doesn't blow, or it's not sunny, or there's a sudden demand for power, we don't have that capacity when we start getting into larger renewable energy within the grid. So we really need to start thinking more about how we're going to balance the supply and demand for power. Just a quick slide here to talk about variability and predictability. So we all know solar panels produce no power at night, but they tend to be predictable otherwise. There's variation between seasons, and there's reduced output in winter. Wind energy, on the other hand, tends to have moderate variability. The wind can be blowing at any time, day or night. However, it's more difficult to make predictions about wind, where there's going to be windy at a particular site throughout the days, weeks, and months. On the other hand, tidal energy, which is used in coastal areas, it has high variability since there's no power when the tides aren't going in or going out. But it's also the most predictable phenomena. In fact, you could set your clock to it. So coastal areas experience too high and too low tides every 24 hours and 50 minutes. Some of the characteristics of VREs. So let's talk about traditional sources first. So traditional sources where mechanical power is converted directly to AC electrical power at the grid frequency of 50 or 60 hertz. So conventional generators have a stationary part called a stator and a rotating part, the rotor. So the speed of the rotor is synchronized to the AC frequency of the grid. So one of the features is it has a large mechanical inertia that's capable of storing kinetic energy. And so this inertia helps to avoid undesirable frequency variation. So, and all the generators on the grid work together to help keep each other synchronized. Now, with VRE sources, they're non-synchronous. So they depend on power electronics, an inverter or power conditioner to convert the generated electricity into the correct voltage and frequency of the grid and to synchronize it with the grid. So VRE interface to the grid using power electronics. So there's no, it's not directly, the power source is not directly coupled to the grid dynamics. So there's no mechanical inertia capable of reducing fluctuations. And even say wind turbines that use a rotational movement to produce electricity, the rotor must be allowed to turn at different speeds. So it can't be a synchronous generator. So wind turbines use what's known as a three-phase asynchronous generators, which have mechanical properties that are useful for wind turbines, like generator slip. So where the rotor is allowed to turn at a different speed without stressing the structure of the generator. And for managing variability within the grid, there's a couple of techniques, a couple of points I want to make. Diversification of technology types and geographic locations. So obviously, if you have a large country like the United States, you know, the wind could be blowing at any given part of the United States. And same thing with the sun. It may be sunny in one state and not sunny in another state, vice versa. So we can achieve diversification of, we can manage the variability with a large distributed power grid. But this is very difficult to achieve with small isolated grids. So improving transmission of power is also important to better integrate these VREs. So when you have the large quantity but small capacity, so you want to have improved transmission between your power sources. And of course, managing demand. There's consumer incentives to shift usage away from peak demand. Real-time variable electricity pricing, for instance. And last but not least, there has to be energy storage. And some of the types of energy storage, I'll go in the next slide. For instance, pumped hydroelectric, or it could be an electromechanical system, or electrochemical, or thermal. So if we look at the energy deployments, energy storage deployments in the United States, in 2020, the storage capacity was right around 23 gigawatts, and the generation capacity was 1,100 gigawatts. So one of the types of storage is pumped hydroelectric. So this is when, during low demand, electricity is used to pump water up into a reservoir. And so during times of peak demand, the water is released from the reservoir and it turns a turbine and generates electricity. And this has been around for decades, in fact. The first recorded use of pumped storage was in 1907 in Switzerland. So they can provide massive amounts of power for very long periods of time. And as of 2020, in the United States, around 94% of grid storage capacity was made up of pumped hydroelectric. But in terms of building new facilities, there are geographical limitations, and most suitable sites, as I mentioned, have already been developed. Compressed air storage, this is an interesting one. This is where electricity is used to compress air at up to 1,000 pounds per square inch. And then it's stored usually in like an underground cavern. So it's also very dependent on site. So when the electricity demand is high, the pressurized air is released and it turns a turbine and generates electricity. But there's only 2 plants in the entire world. One of them is in Germany, and there's another one in McIntosh, Alabama, that can produce 110 megawatts. And I believe that one in Germany is right under 300 megawatts. We then have molten salt. So molten salt is a type of thermal energy storage where they use salts that have high boiling points like sodium nitrate and potassium nitrate. So these salts are heated and stored in an insulating container during off-peak hours. And when energy is needed, the salt is pumped into a steam generator that boils the water and spins a turbine and makes the power. So they tend to be used with solar thermal plants where these parabolic mirrors track the sun and concentrate the heat to heat up to produce the power and to heat up water for the turbine. And also with nuclear reactors. And thermal systems can also include using electricity to cool water or produce ice, for instance, when it's used for cooling during periods of peak electricity consumption. Flywheels, on the other hand, with flywheels, the electricity is used to spin a type of a rotor inside a low friction housing, and usually they operate in a vacuum. And so they have very low friction magnetic bearings to maintain the inertia. And so when power is needed, the rotation is used to turn a generator. But with this type of system, the discharge times are very, very quick. You're looking at in the 8 to 30 seconds. So they're more for power management and managing fluctuations and instantaneous load rather than long-term storage. Then we have batteries or electrochemical systems. So very large batteries can store electricity as needed, and they have a huge potential for growth. And they're ideal, in fact, for variable renewable energy systems where they can be located close by to the energy source. And these systems can use lithium-ion, they can use lead acid, and other battery technologies. And efficiencies can be around 60 up to 95%. So currently, batteries make up only around 3% of the total grid storage in the United States. But when we consider that large-scale battery storage deployment only dates back to 2003, we can see from the chart here that from the table here that the installed deployments have been growing at a very rapid rate as the technology and the costs improve. And at this time, we're going to go to a quick live poll before I hand it to Jill. So live poll, let me see. So here are the questions. What interests you most about this webinar? To learn about renewable energy in general, or to learn about lithium-ion batteries, or interest in test and measurement methods, or my manager made me do it, or something else. The next question is, what is your company doing to support the transition to renewable energy? We switched to 100% renewable energy, or we're in the process of switching to renewable energy, or we're trying to make our energy uses more efficient, or we have a sustainability program in place, or nothing, or not applicable. And the last question is, what is your level of understanding of the topic? I'm totally green. I have some basic knowledge. I have solid background, or I'm an expert. So we will let the poll run for just a couple of moments and see what the responses were. Okay, I'll just give it one more second. And okay. So for the question, what interested you most about this webinar? The largest answer by big margin was to learn about lithium-ion batteries. And this doesn't surprise me at all, because as we've seen, this is a field that's growing very, very quickly. So for the next question, what is your company doing to support the transition to renewable energy? And most people are saying NA. After that, we have about 20% saying they're trying to make the energy usage more efficient, and 18% saying that they're trying to, they're in the process of switching. And interestingly, nobody has achieved 100% renewable at the moment. And finally, the last question is, what is your level of understanding of the topic? And most people seem to have some basic knowledge. Thank you. So with that, I am going to stop sharing the screen and I will pass it on to Jill.
Hello, everyone, and thank you, Isan, for that incredible presentation to really set the stage. I'm going to share my screen right now. All right. So as everyone was saying, today we're talking about lithium-ion batteries and the renewable energy future. And Isan really told us how variable renewable energy, right? We need energy storage for solar, wind, hydro, these variable sources. And so I want to take this conversation a step further and talk how lithium-ion batteries are playing such a large role in this shift. And before I start, I just want to say it's incredible to have this opportunity to talk to you all live. I talk to you all if you engage with my Instagram or my Twitter, my YouTube channel, and I really love like meeting everyone I've met through those. And so I just want to say, feel free to reach out to me, subscribe to my YouTube channel, and I'm happy to take more questions. If you're not in this live session, but coming in, watching this after it's been filmed, you're still welcome to reach out with any questions you have. And I'll have my contact information on each slide so you can contact me. Let's get started. Okay, so the current state of the rechargeable battery market is the first thing I'll go through. And this branches off of Isan's first presentation. Then we're going to do something really fun, okay? We're going to do an interactive simulation, and I'm going to need your participation for this. So get ready for that. And I'll finish with the importance of battery sustainability and recycling. I think as we're moving towards a renewable energy future, we're going to see a lot more focus on making sure that the supply chain for batteries is sustainable, and that includes battery recycling. The rechargeable battery market in 2019 was $89 billion US dollars. $89 billion. This is a huge industry. And you can see that in this graph on the left here with the billions of dollars versus the year, we've seen such a large growth. It's been an 11% average growth per year. And this includes all rechargeable batteries, not just lithium-ion batteries, okay? And in that graph, you'll see that the largest portion, that lime green, is SLI, which stands for start, light, and ignition batteries for vehicles. So those are like your lead acid batteries in your car today. Then you see around 2013, 2010, 2013, this rise in industrial batteries. And these are the stationary storage batteries mostly that Isan was talking about. Actually, it's not mostly stationary storage, it's actually mostly forklift vehicles. And then starting in 2013, we see the rise of automotive batteries for automotive purposes. And I think this is such a hot topic right now. We're definitely hearing a lot about Tesla in the news, as well as other companies converting into their vehicle lines into electric vehicles. And this is happening over the whole world. I think we all know that at this point. And this graph on the right really summarizes, I think, an important point that we're not just seeing this growth of lithium-ion batteries, we're also seeing a growth in other battery types as well. And lead acid batteries really have the majority market share. However, lithium-ion batteries are the fastest growing market. And this is just going to keep increasing. This graph is only up to 2019. And on the next slide, let me show you what's going to happen. This is crazy. So there are major influences happening in the battery market that are accelerating this growth. The top three is the mobility and energy solutions for population increase and city growth. Our cities are booming and our populations are increasing, and we need better mobility to move around through the cities, hence the advent of electric vehicles, which will enable self-driving cars. The second thing is the shift in energy production to renewables. Just like Isan was talking about, we're getting more solar, more wind projects, more hydro projects, and others as well. And this is mainly because of this last point here, this climate change related emissions reductions. So we all have probably heard about the Paris Climate Agreement, and there's other government regulations happening all over the world, including in China, that are really setting the stage for pushing all of this emphasis on transitioning to a lower carbon footprint, right, around the world for all these industries. And so we need energy storage in order to allow access to these variable renewable energy sources and make sure that they can power our day-to-day lives. This graph on the right is insane. Okay, so here's the planned lithium-ion battery gigafactories up till 2028. So this is a projected amount. And you can see in red is the 2018 active capacity, and in yellow is the capacity that's projected to be in 2028. Look how many gigawatt hours we see there. It's just going to be booming. There's so many lithium-ion batteries that are going to be produced for all of these applications. So those graphs I showed on the previous slide, we're just going to see this battery market increasing, expanding with time. This is just the beginning. Now, since this is just beginning, this is an incredible opportunity for business, right? There's so many problems to solve in this whole battery process. So why don't we all start a business right now? Okay, now this is a joke. This is kidding, but this is time for our simulation. You guys ready? So welcome to Pestana Enterprises. This company, our mission is to create a sustainable zero emission world through clean energy solutions. And you are hired. I'm going to hire all of you to be the VP of engineering. And I have an important assignment for you, okay? You're going to be tasked with selecting the right lithium-ion battery material for our clean energy storage solutions. So this is where I'm going to need your participation, because we need to be able to create clean energy solutions that are also sustainable. So I know some of you just have a basic knowledge, and so I'm gonna do some onboarding for you to bring you up to speed to where we are today. So what is a lithium-ion battery? Lithium-ion batteries are energy storage devices, and they store energy in a chemical form. And you can see in this graph, or this diagram on the left, we have a diagram of a lithium-ion battery, and this is just representative. In this battery, you have 4 main components. On the left side, you have the cathode, which stores the amount of lithium that's going to be used in the energy of the battery. And so the amount of lithium stored in the cathode is typically the amount of energy that the battery has. That's very important. The second part of the battery I'll talk about is the anode. So the anode stores the lithium from the cathode when the battery's fully charged. And so the anode needs to store that lithium. And then the electrolyte is selected. Typically, it's a lithium salt in a non-aqueous solvent, which means that there's no water in this electrolyte. And there's also additives to help with safety and improving the cycle performance of the battery itself. And finally, we have the separator. So the cathode and anode are conductive. And if we have them touch, we'll just cause an explosion, basically. So we need to separate them with an insulative separator, an electrically insulating separator. And this can be made out of a polymer, a ceramic, or a blend of a polymer and ceramic. So lithium-ion batteries, when we say lithium-ion batteries, it could mean a variety of different materials specifically, but they all have that same root of that lithium-ion is the atom that's being used to store chemical energy. So here are some of the cathode active materials and anode active materials that are commonly used today. For cathode active materials, many are nickel-based, which include NCM, NCA, NCMA, and then a couple other ones are lithium cobalt oxide and lithium iron phosphate. There's many more than this, but these are primarily used in industry today. And for the anode active materials, we have graphite, which is a form of carbon, as well as silicon or silicon oxide, lithium titanate, and lithium metal. Now, the majority of cells that are on the market today use graphite anodes with maybe a little bit of silicon additive if the company's a little bit more advanced in their anode production. So there's so many materials that are selected for batteries, right? And our company needs to make these sustainable energy solutions. And so we need to pick the right materials for our specific applications. And that's why I need you all, my VPs of engineering. So my first question to you is, which cathode would you pick for a stationary storage battery? Now I have a little cheat sheet for you. And in this cheat sheet, you can see a diagram, the hexagon, where each point is a specific property of the cathode that's important for cathodes. So in the top, you have the specific energy in watt hours per kilogram, and then you have the specific power in kilowatt hour or kilowatts per kilogram. Then you have the safety. So this means if it's fully maxed out, it's the safest material itself. It's non-toxic. When lifetime is maxed out, that means that it can last a very long time inside of the battery. The cost, having the cost all filled out in the hexagon, means that it's low cost. And then combined just means all those properties are great for that battery. So you can see that perfect cathode is all maxed out. And then the other options we have are NMC, NCA, LCO, LFP, and LMO, lithium manganese oxide. So this battery for stationary storage, we want it to be low cost, safe, and we want it to last, let's see, many years and store energy generated from a wind turbine in Tehachapi, California, which is the town where I grew up. We have a lot of windmills in Tehachapi, and so I have a picture there for you. So this battery energy storage battery is going to be used to store wind energy and needs to operate in temperatures from 20 degrees to 100 degrees or -6 to 38 degrees in Celsius. So go ahead and fill out that poll with which cathode you think would be best for this specific application. And the second question will be on the next slide. So if you already answered that, you're a high achiever, you know you're going for it, but on the next slide, we'll answer the next question. So just for now, answer that first question. Okay, I think we can stop. And honestly, I'm just gonna leave. Okay, great. So for that, we see most people picked LFP. Let's see what we have for the results. So yes, LFP is probably the best material based on these data in order to pick for this specific stationary storage battery. In fact, if you selected that, you could be the VP of engineering for Tesla if you wanted, because that's the decision they made recently for their megapack installations. So they're going to be using LFP batteries for their grid scale battery storage systems. And the reason this is because LFP is set to overtake NMC in production by 2030 for these stationary storage systems because it's safer. The cost of it is decreasing compared to nickel-based and cobalt-based cathodes. And finally, something interesting is that China's ownership of the intellectual property surrounding LFP technology actually expires in 2022, which is going to open the doors for a lot of businesses to use this material. So the next poll we have, the next question all of you VPs of engineering need to answer. So which cathode would you pick for a sports car? We picked a cathode for the stationary storage, but we have different requirements for a sports car. This battery is required to enable superior vehicle performance and have a lifetime of about 8 years. So go ahead and fill out this poll. Which do you think, for question number 2, which cathode material would you pick for a sports car? And this is a little bit more difficult, I think, than the previous question, because it's maybe not what you would expect. Unless you're in the industry and you already know what's being picked for these vehicles, then you may know the answer already. So we'll leave that up for a little bit longer. I trust you all. You all are smart. I know you're capable of making decisions for this company, driving us towards success, meeting that bottom line, meeting meeting our goals. Amazing. Okay, I think we can stop the poll now and see what the result is. So we see most people chose NCA, nickel, cobalt, aluminum. And second most is, it's tied for LFP and NCM. Very interesting, very interesting. I like this decision though, I really do. And I think either NMC or NCA would be the best option. And now you may go, well, the safety isn't that great or the lifetime isn't that great. Well, for a car to have the best performance, the parameter that really matters is its specific energy, because specific energy is basically how much energy per kilogram that battery has. And a car needs to be able to move and perform, right? And it can't be weighed down by a heavy battery. And so there's a lot of improvements that need to happen with using high nickel based cathodes, but it's a great technology to implement into the sports cars. But those of you who picked LFP, you're not too far behind. In fact, a lot of vehicles are being made with LFP. I'm sure many of you know that. And even Tesla, some of the vehicles are made with LFP now. So those vehicles, though, are more for like a shorter range and for a wider consumer base because they'll be lower priced. So great job, everyone. Congratulations, you completed your first 2 assignments. Well done, well done. I'm really excited to see that so many of you picked such great options for our company. I know we're going to succeed with you on our team. But, we said our company was going to make these energy storage solutions, but we also have to make sure that they're sustainable with 0 emissions, right? And so how can we make sure that our supply chain is able to have from cradle to cradle, essentially, instead of cradle to grave, the actual recycling process of a battery be sustainable and ethical? Now let's talk a little bit about the sustainable battery supply chain. A tool that we use to analyze whether something is more or less sustainable is the life cycle analysis. And I was taking a green engineering course in graduate school when I learned how intricate a life cycle analysis can really be, and how when you're looking at a life cycle analysis, it's really important to tune into how that company is performing the analysis. For instance, the example I was shown of a life cycle analysis was between a Prius, a hybrid electric vehicle, and a Hummer. And they were questioning, which is more sustainable? Is it the Prius or is it the Hummer? And the result of the analysis showed that the Prius was worse for the environment than the Hummer, that the Hummer was more sustainable. I was flabbergasted at that. I mean, why would that happen? Well, it turns out in digging into the life cycle analysis, what they did was they found that the Hummer would last twice as long as a Prius on the road. And so that means it took 2 Priuses to match to 1 Hummer's life cycle or lifespan. And so the analysis was actually between 2 Priuses versus 1 Hummer. Yeah, so not actually, I mean, this analysis in particular was done by somebody who was selling Hummers. So they were biased in this. So it's important to look at how the life cycle analysis is completed to form any conclusions as to which is the most sustainable option. But in general, on average, electric vehicles are 2 times better than ICE or internal combustion engine vehicles, as long as these conditions are met. The first is that the vehicles must use electricity from renewable energy sources and or from hydrogen from 0 emission sources. The second criteria is that if you have a hybrid electric vehicle, you must use it on its electric mode for the majority of time. The third part of this puzzle of making sure that electric vehicles are sustainable is that the electric vehicles must be basically part of the grid scale energy storage or their smart charge to preserve that grid balance. And the fourth is that the batteries must be recycled efficiently, which I'll talk about more in a moment. And so if you see this whole picture of what it takes for electric vehicles to really be sustainable, we see that this comes from different sectors having to work together strategically to make these outcomes a reality. And that includes sectors like transportation, energy, construction, and infrastructure. And the other thing I want to add to this is that in all these decision-making processes, we need to include diverse people for making sure that we're making the best decisions for our communities and for our world, and ensuring that we're positively impacting all humans and environmental life. You'll see that the battery industry now is not very diverse. It's very homogenous in its demographics, and I'm hoping to be part of this change in the industry. And I think we can go a long way just by including diverse voices into these conversations. I mean, if you have just the same few people making decisions for everyone, you may not have the best decisions being made or the wisest ones for a long-term future. And there's so many companies right now working on this part of making sure that these fields are diverse and inclusive, and companies know how to make business decisions and business models around inclusion of their employees and people. There's companies like the one I created, the STEM Thrive Guides, as well as there's one called Career Agility, there's Metaspace, and there's Every.1. There's so many companies that are coming out that other companies can hire and use in order to improve their bottom line through diversity and inclusion practices. And I think that's an essential part of making sure this battery supply chain is sustainable for long term. And it's a part that's so easy to do. It's so easy to do, at least compared to some of the other problems in the field, right? It's very controllable for a company to do, and it really benefits everyone in the picture. So I just want to emphasize that we can't just think of technological solutions. We have to also innovate our workspaces and how we're including different people's voices into the decision-making process. Now, battery recycling is a major concern for the industry today. And this is because a lot of the materials, especially nickel and cobalt, which we talked about earlier, that are cathode materials, are precious metals that are being mined throughout the world, but often in regions where there's conflict. And so the cost of these is it varies a lot, and it's not a reliable source to mine it from certain regions. And so to not only make sure that we're getting a sustainable raw material supply chain for these batteries, but also make sure that we're not being unethical in our sourcing of materials for batteries, and we're being sustainable in our whole battery life cycle, we need to incorporate battery recycling into the picture. And there are companies working on this currently. And the whole principle around battery recycling is that a battery would not just have a first life in an electric vehicle where its state of health, or SOH, would be 100%. But then once the battery has been used for a while in that vehicle and the state of health has decreased to about 70%, it can then be put into its second life in a stationary storage battery for 5 to 10 years. And then from there, as it's used in the stationary storage for some time, then it can go through the recycling process once it reaches about 40% of its state of health. And then from there, the raw materials can be extracted and processed and made into new batteries once again. So right now in the industry, we're talking about the future, what's going to happen in the future. Right now in the industry, we're seeing this explosion in batteries being produced by these gigafactories that's going to happen for the next decade. But then we're going to have so many batteries, right? And the raw materials from these batteries, it may be harder to get those raw materials to support this accelerated growth. And so we're going to see a more latent acceleration in battery recycling in the next decade or two. So that's really where I hope, at least, the battery is headed, is towards more and more recycling and sustainable practices around that. And the state of health, when we think about us battery scientists and testing engineers and people with the utility, the whole ecosystem of batteries is going to revolve around the battery state of health and optimizing the battery state of health so that we get the most out of our batteries when they're operating in a vehicle, in stationary storage. So I want to talk about that for a second before I turn it back over to Isan. So the state of health of a battery is the relationship between the current performance of the battery and its original performance or the design specifications. So a new battery, like we said, has 100% state of health, and a battery that has zero charge, no capacity, 0% state of health. So this is opposed to the state of charge. State of charge is just like when you have your cell phone and it dies for the day, it's at 0%, but then you can recharge it to a state of charge of 100%. State of health is different. So on my smartphone, at least, I can go into the settings and actually look at my battery state of health. And go ahead after this talk, go check out what is your battery state of health in your phone. And so there are techniques that companies currently use to monitor the state of health in your devices and in vehicles as well. And I think this is one of the many areas, obviously, for growth in this sector, is using different kinds of analytical and testing techniques to monitor battery state of health. One of the tools that I'm seeing a lot of growth in different startups that are coming up is using electrochemical impedance spectroscopy, among other electrochemical techniques, in order to monitor the state of health of batteries while they're functioning in a battery pack in whatever application. Now, electrochemical impedance spectroscopy, or EIS, I won't be going in depth in that here. I have a YouTube video that goes more in depth with that. And I have some other videos that explain like a Nyquist plot. So go ahead and check those out after this webinar. But I just want to say about what electrochemical impedance spectroscopy is and how that relates to the state of health of the battery. So electrochemical impedance spectroscopy measures the impedance of a battery or its internal resistance. And so it can give you information about how the battery's components are degrading and breaking down. And this graph here on the right is a Nyquist plot of the battery EIS data. And all I would like you to know at this point in time is that the lines you see, the curves you see on this graph, represent the impedance of a single battery that has been cycled during certain intervals. So in black, you have the first cycle, red is the 50th cycle, green is the 100th, and a cycle means it's been charged and discharged once. And so you can see they have the data, the impedance data, all the way up to 800 cycles. And at 800 cycles, this battery most likely has a decreased capacity, or its state of health has suffered and it's lower percent than the original 100%. And so when we have, sorry, I have a message. When we have the state of health changing over time and we're monitoring with EIS, we can get a lot of data about how we can optimize a battery in real time. And people are starting to use machine learning and artificial intelligence in order to take the real-time EIS data or other electrochemical data from the battery management system, or BMS, and then filter that into how the BMS is operating and maintaining that battery and how it's charging and discharging those batteries and optimizing those battery pack cycle life in the long term. And this, I think, is like I said, is just the beginning. We're just at the beginning of doing this monitoring of state of health of battery in real time. And as Hioki, as Isan will say, and Hioki has a lot of test equipment based on monitoring properties like these of the cells. So thank you so much for listening to my presentation. And I will turn this over to Isan, who will conclude, and then we'll go to a Q&A.
Thank you so much, Jill. Let me go ahead and reshare my screen. That was an awesome presentation. Thank you. I think we've already completed the portion of the live poll. So I just want to talk about this slide. So this is an overview of Hioki's solutions for lithium-ion batteries, in particular in the manufacturing of battery cells, modules, and battery packs. And the process can be kind of roughly broken up into several different steps here shown in the arrow. For instance, the manufacturing of the electrodes and the materials used for the battery. This is very important. I mean, you have to start with the right quality materials in order to create your battery. And there's an example here. This is a very specific test and measurement system, the RM2610. It measures the electrode resistance the electrode sheets. Then when we get to the assembly of the battery cells, for instance, inspection of the welding and checking for metal particles, etc., Hioki also has test solutions for that. These instruments tend to also be used in different types of situations. For instance, the resistance meter that can measure in the ohm or nano ohm resistance range. And so for performance testing of the finished cells and for cell sorting, we have a number of different test solutions. The battery testers, for instance, they test the AC-IR method using 1 kilohertz test signal. And for doing more in-depth analysis, for doing frequency sweeps, the Nyquist plots and co plots, we have two systems, the battery impedance meter and chemical impedance analyzer that can create a Nyquist or co plot so you can see the state of health of the battery. And then finally, we have the assembly of the modules and then performance testing of modules and packs. And that could involve inspection of the packs, inspection of the battery management system, the circuit that goes into the packs. And we also have high volume test capability using ATE test solution. Now, I'd also like to mention that sometimes customers have very specific test requirements that involve AC-IR or doing a Nyquist plot or a co plot using very high test voltages under very high current loads. And Hioki has an in-house metrology lab that's capable of developing very customized test solutions. And the example here shown is the active line battery analyzer, or the ALBA. And this system is based on one of our existing off-the-shelf power meters, power analyzers, the PW6001. It's been customized in this instance. And using different PC applications and custom electronic load and signal generator, et cetera, we've been able to develop configurations where co-plots can be generated under very high current and voltage situations. So this system is not shown on our main website. So this is something that is customized for different customers. And I have a quick Q&A session here at the end.
Hey, Jill, Ishan, thank you very much. I certainly learned a lot in this presentation. I really appreciate that. I will be moderating the Q&A session. Let me see what came in. There are quite a few questions that we had during the presentation. Some got answered. I will read the questions anyhow, just in case not everybody sees the answers. First question, how do you decide the future of battery chemistry for lithium-ion in stationary storage? Is it going to be LPF, lithium iron phosphate, or NMC, so nickel, manganese, cobalt? And I think this question, Jill, you answered that in all depth with the radar chart. Again, we have the webinar recorded, so if you want to go back and be the CTO again of the company, feel free to go back to our website and download the webinar. But Jill, any quick answer to that, LFP versus NMC?
Yeah, I just want to add that while we did that exercise and it came out that LFP was perhaps the best cathode based on the parameters that I showed, there's still a market share that nickel-based cathodes will hold for the stationary storage space. And especially since we're seeing electric vehicles with nickel-based cathodes still being produced and everything, we're still going to see that second life of those batteries be put into storage. And so there's going to be a mixture of different chemistries for stationary storage, but it seems like the most dominant one will be LFP, at least in the next decade.
Thank you very much. Awesome. Next question, let me move on here. What are different criteria to regulate the C rate, so the capacity of the battery? Now, this sounds like a very wide question with a lot of answers. So is there any 2-minute answer to that broad question?
So if I heard it's right, it's how do we like monitor, regulate the C rate of a battery?
I think he's looking for what determines the capacity C rate of a battery. I think that's what
Okay.
the question means. I don't know, but that's my interpretation of the question.
So I'll just answer with, we determine what the C rate is based on the application. And so if we need a C rate, for people who may not know, is just the rate at which you charge or discharge a battery. And I actually have a video about calculating the C rate on my YouTube channel. So if you want to check that out, you can go ahead and watch that video, which describes it more in depth. But generally, you could pick any C rate you want, but you have to make sure that the chemistry of your battery is equipped to handle that kind of C rate, or else you're going to have issues like lithium plating, or even like thermal runaway, or other issues as well. So you want to make sure that you're using the correct C rate for the battery chemistry.
Thank you. And related to that is a question: somebody's watching YouTube videos and sees the spectacular explosion of lithium-ion batteries. So why do batteries catch fire, and what can you do about it?
So when I was talking earlier about choices for materials for batteries, one thing I didn't really mention was how thin these materials are for batteries. And I didn't mention a current collector is the foil at which the anode or the cathode is put onto. And this current collector is a thin foil. Now, you might have heard a few years back with like the Samsung battery fires. Those are probably caused by the materials inside of the battery being too thin, so that as the battery is operating, those break down, and then you have the anode and cathode actually touch, which causes a short circuit, a spark, and then the electrolyte inside of the cell is flammable, and so it can actually catch fire and explode. And so when it comes to flammability, what can cause this is the shorting of a battery using materials that break or degrade, or something happens to ignite the electrolyte of the cell and cause an explosion. So it's definitely an issue that unfortunately tanks companies. So it's a lot of companies really pay attention to safety.
Yeah, and from the measurement perspective, we see a lot of test equipment being sold into battery cell testing before they actually get filled with electrolyte to avoid these shavings and shortings to happen. So that's there too. And the industry has come a long way in the past to prevent or reduce the number of explosions. Oh, here are some fun questions about more the visionary part of the battery business. Two questions in the same theme, on the same gist about fuel cells. How will fuel cells replace lithium-ion batteries in the future? And solid-state batteries. Will solid-state batteries challenge lithium-ion batteries in the future?
Those are great questions. And actually, when I was starting out as a battery or a scientist, I did research at NASA Jet Propulsion Lab on fuel cells. And what I love that experience, but what I took away is that fuel cells weren't quite as ready as batteries to be in the market in vehicles. And this is because they're still pretty high cost. They are still pretty heavy and bulky. But there are fuel cell vehicles out there. I think there's going to be a market for that. And whether it increases is more based on if we can lower the cost for that, to enable that, and also lower the cost for hydrogen generation and storage. So there's definitely going to be that sector out there, but its speed depends on this research of materials that we're seeing. And then for solid state batteries, those are still in development, and there's a lot of buzz around those, a lot of investments being made in companies that are working on solid state. And so we'll eventually see solid state. As far as when, it's hard to say whether it'll be in 5 years, 10 years. I think we're just going to have to wait and see, but it'll happen.
Another related question: if a battery starts burning, you cannot use water to extinguish them. Do you have any suggestions or idea how to make safety concepts in such situations?
Yeah, there's a lot of design that goes into battery packs nowadays to make sure that if a battery were to catch fire, it can maybe self-extinguish through the pack itself. And yeah, you don't want to spill water on a battery. That just will fuel the fire, and there's specific actual like fire extinguisher. I think it's D-rated fire extinguishers that are specifically for electrical fires like battery fires. So knowing that safety is important. Yes.
Okay, two more questions that I see here about state of health of batteries. One question related to an piece of equipment, Ishan, you showed impedance spectroscopy up to 100
Yes.
amps and kilovolt. Where can we get more information on that?
Yeah, the ALVA system is a custom implementation. It is a custom implementation. So it's something that Hioki would work with the customers, trying to understand what their requirements are. And then we would kickstart a project specifically for that customer. So what I would say is just contact us, drop us an email, drop us a line, and let's get the communication going and find out what we can do to help you guys out.
All right, thank you. And here another question. Man, this question comes in. I think we're getting to the end of the list here. What equipment does Hioki have to check the state of health on batteries?
Well, we have the BT4560 battery impedance analyzer, and we also have the IM3590, which is a chemical impedance analyzer. And so they're basically able to use an AC test signal and sweep between the milliohm range all the way up to about 1 kilohertz. And you're able to produce a Nyquist plot or COCO plot within a matter of a few minutes. So that's very, very handy. So definitely those instruments can be used off the shelf for very quick analysis of batteries.
Thank you very much. Last question that's coming in. So if you have more questions, you know how to contact us, you know how to contact Jill. Feel free to use our websites or the contacts that we have given in the webinar. Last question here, that's another visionary question. Where does graphene-based and nanowire-based batteries stand in the future of these applications?
So these are graphene and nanowires are incredible materials, very interesting materials with their properties and high potential for applications like in batteries. The concern for this is the cost it takes to make like pristine graphene and to make nanowires is currently way too high to incorporate into this large scale production of batteries. And so once somebody solves the problem of how to make cheap graphene and cheap nanowires, we'll see that. But until then, we probably won't see that at least in the majority of mass-produced batteries out there.
Thank you very much. With this, we have all the questions. Just want to remind everybody, our contact information is here. Jill's YouTube channel is across the nanoverse, not the universe, but the nanoverse. I think that's what it is, right, Jill? So there was a question.
Across the nanoverse, because I study everything on the nanoscale. So
check it out. I want to thank all you all for participating in the polls and in the CTO exercise. Thank you, Jill, for this outstanding talk. Thank you, Ishan. And please sign up for our next webinar in the same channel. Thank you very much.
Yeah, thank you all for hosting me. And thank you, Jennifer, Isan, Chris, Kevin, Barry, Yumishi, for all hosting this. This was incredible. And thank you so much for providing this space to have this conversation.
Thank you, everybody. Bye-bye.